Hi, welcome to week 4. I'm Claire and we're going to be looking at vibrations and waves this week. But first, just a bit of recap of the maths that we're going to be using. So when it comes to vibrations and waves, we are going to be using a lot of sines and cosines, so it's a good idea to just do a bit of revision. The first thing is to make sure that you know how to sketch these functions. So if we want to sketch the graph of sine of t, we have the t-axis is where we would usually see our x-axis, and our x-axis is what you might usually think of as the y-axis. So we're looking at how x is changing over time, and if x is changing as sine of t, then when t is equal to 0, our x is equal to 0, then it starts oscillating up, then it oscillates down, oscillates up, and it keeps going on infinitely. And in fact, we should sketch that it has in fact been doing this oscillation since negative infinite time. A couple of important points on this particular graph. The maximum value of sine of t is 1 and the minimum value is -1. And if we measure the distance between any two peaks, so this peak and this peak, or for example that peak and that peak, it's always going to be the same value. It's going to be 2 pi if we're measuring in radians. You might be more familiar with saying it's 360 degrees, but we're usually going to be using radians in this course. Now, the graph of cosine of t looks almost exactly the same. It's in fact just a slightly shifted version. So we have the same axes, we have t and we have x. And then for cosine, when t is equal to 0, x is equal to 1, and then our function oscillates down, moves up, and it keeps doing its thing. And just like sine, it's been doing it all the way since time began. It has the same maxima and minima, and it has the same period of 2 pi. So those two functions you need to be able to draw pretty much in your sleep. In fact, if someone wakes you up at 3 a.m. in the morning and says, draw the graph of cosine of t, then you should be able to just do that, roll over and go back to sleep. But we are also going to be needing some shifted and scaled versions of our sines and cosines, and you need to be able to sketch those. But to help with that, I've put together a little app in GeoGebra which will help us explore what the various constants do when we multiply and add them within our sines and cosines. So let's have a look at that quickly. So here I'm plotting two graphs. You can't actually see the blue graph because it's hidden under the yellow graph, because at the moment our g of t, which is a sine omega t plus 5, 0, has an a of 1, an omega of 1, and we're not adding anything, so it's exactly the same as the blue graph. So let's see what happens when we increase the amplitude. So I'm going to take my amplitude up, all the way up to 2, and you'll see what's happened is that every value of the blue function has been multiplied by 2. Well, actually 2.1 here. So our new amplitude is sitting at 2.1. So as soon as we know that a is 2.1, we know that the maximum of our sine graph is going to be 2.1 and the minimum will be minus 2.1. But we don't only increase our amplitude, we could also scale it down. So for example, we might have that our amplitude is 0.5, and now you can see that the maximum value of our green graph is only half that of the original blue graph. And there's no reason why this has to be positive. So we could, in fact, take a negative value. And then you'll see what happens is every positive value of our original blue graph now becomes negative and scaled by the appropriate amount. Okay, so let's put our amplitude back to 1 and see what omega does. So this is called our angular frequency, and it's usually denoted with an omega, which is a Greek letter. And when omega is equal to 1, our two graphs are the same. But now let's see what happens as we increase omega. So you'll notice that I'm now getting more oscillations of my green function over a period of 2 pi than with the original blue function. And that's what the angular frequency does. It measures how many complete oscillations, so complete up and down and up again, of our function are completed within a time of 2 pi. So you'll see the more I increase my angular frequency, the more complete oscillations I get between 0 and 2 pi. But just like with our amplitude, there's no reason why we only have to increase omega. We could also decrease it. And now you'll see that as we decrease omega, we're getting not even a complete oscillation in the time period 0 to 2 pi. So here with an omega of 0.7, my green function is only completing 0.7 of a full oscillation over the time period 0 to 2 pi. And in fact, to complete the full oscillation, it needs almost 3 pi time. Now, I could have also had negative omegas here. You can think about that for yourself and figure out what that means, but I think we've got the general idea. Okay, so we're going to put omega back to 1. And now let's see what phi does. So phi 0, which is called the phase angle, let's add a little. And you'll notice that as I'm increasing phi, my function appears to be shifting to the left. And if you've done any shifting and scaling with functions, this will be no surprise. When you add something to a function within the t term or the x term, if you're thinking about functions, y is equal to some function of x, then you shift to the left. On the other hand, if you subtract something, so now I'm adding a negative here, then it shifts my function to the right. So we'll talk a little bit more about that later, but these are the basic 3 things that we need in order to modify our sinusoids so that they are really super useful for the kind of motion that we're looking at. And you can do exactly the same thing with cosine. Remember, cosine is just a shifted sine. And in fact, you can see that if we shift our sine wave by, I can't quite get exactly half a radian, but there we go, there we've got a cosine made out of our sine wave. Okay, so make sure that you are very comfortable with sketching your sines and cosines, both the originals and the shifted versions. And after that, it's time to think about differentiating them. So the next thing you need to be able to do is to differentiate functions involving sine and cosine. So just a quick reminder there. If we've got x is equal to a sine omega t plus phi 0, and we want to differentiate that with respect to t, so this should actually be a t there. Then we have dx by dt is equal to, well, we've got a multiplying our function sine, so the a is just a constant, it comes along. We want the derivative of sine, which is minus cosine. And then we want omega t plus phi 0, and we're going to multiply that by the derivative of omega t plus phi 0. Now remember, t is our variable, omega and phi 0 are both constants, so that derivative is just omega. So just rewriting slightly, we get that the derivative is a omega cos omega t plus phi 0 with a negative sign. So make sure you're happy doing that. Just for kicks and giggles, I suggest that you also try taking the second derivative, because we are in fact going to be using that a bit later. And then make sure that you can do the same for cosine as well. Once you're happy with differentiating, just a brief note that mostly we'll be using radians. So it's important to know which your calculator is set to. Most calculators have some little button somewhere you can switch between degrees and radians. So just make sure you know where that is, and mostly that we're going to be in radians. Just to remind you, so we know that a full rotation is 360 degrees, but a full rotation is also 2 pi radians. So if you want to think about, okay, what is 180 degrees in radians, it's going to be 2 pi over 2, so that's pi radians, and so on and so on. We all get brought up on degrees, so we tend to say things like, oh, this angle is, I don't know, 60 degrees, because we know them really well, but in a lot of calculations we'll be using radians, so just make sure that you're happy with that. Okay. So what might be a little bit new is that in this lecture, we're going to be talking about solving differential equations. Now, this is a huge topic which you can carry on doing courses in for the rest of your university career, so we're obviously not going to cover everything, but we are going to do just a little bit around differential equations. So let's start by saying, what is a differential equation? Well, it is an equation, so a sum of mathematical terms that is equated to some other sum of mathematical terms. And in particular, some of those terms include differentials. So things like dx by dt, or maybe if you've got different variables, you might have d squared x by dt squared, or dy by dx. So anything that has derivatives of functions. And if you put those together into a differential equation, that's what you've got. Now, this might seem a little bit weird, but actually you've been working with differential equations without realizing it. Because if you have a look at this example that we've got over here, if we think of x as our displacement, then what we're really doing when we write down a differential equation like this one is we're saying there is a relationship between the displacement and the velocity and the acceleration. So all your equations of motion are actually differential equations. It's just we haven't been thinking about them like that. And there are many, many different situations in which differential equations are useful. They get used in population modeling, they get used in chemistry, and of course they get used in physics. So the particular kind of differential equation that we're going to have a look at is pretty straightforward, and we're mostly going to be solving it by the technique called inspection, which actually really means we just make an educated guess and then show that we guessed right. But there are many techniques for more complicated equations, and if you're interested, there are courses you can take on that. But for the moment, just spend some time going through the maths part for this week and make sure that you're comfortable with everything I've discussed so far. When you're feeling good about that, come back and we'll get started on the physics.